Hello everyone, this is Elisa Baum. I am Percona's Director of Product Marketing, as many of you know. We'll begin in just a moment, but first I'd like to conduct just a bit of house cleaning. Could you please help me out by raising your hand using the hand icon located in the GoToWebinar control panel, just to let me know that you can hear me. And let me take a look at you guys. Do I see hands? Yep, okay, I very much appreciate that. Next, during this webinar, you'll be on mute. Should you have any questions at all during the discussion, please enter them in the questions field within the control panel. At the end of the webinar, we'll take as much time as possible to answer your questions, and those that aren't addressed will be answered in a follow-up blog post on Percona's MySQL Performance blog. In addition, I just want to assure everybody that a recording of this webinar will be made available to everybody within 48 hours, and I'll also send you a link to the slides. Okay, so with that said, I'd like to thank you for attending today's webinar, How to Scale Big Data Applications Using MySQL Sharding Frameworks. It's being presented by Justin Swanhart. He is Percona's Principal Support Engineer. And with that said, I'd like to turn the floor over to Justin. Go ahead, Justin.
Hi, my name is Justin. As she said, I'm a Principal Support Engineer here at Percona. I'm not the Principal Support Engineer. I work with a team of folks. I'm also the creator of Shard Query and FlexUse, which we'll not talk about here. So this webinar is going to briefly talk about what is some big data that typically is used with MySQL. Then I'll talk briefly about Fabric and give a brief Fabric example, and then I'll spend some time on Shard Query and talk about what it can do. And then I'll just briefly talk about which solution is best for which kind of data, and then we'll be open for some questions. So what is big data? It's kind of an all-encompassing term for any collection of data sets or any single data set that's so large and complex it becomes difficult to process using traditional data processing applications. Okay, that's the Wikipedia definition. Big data, when we're talking about big data, typically we have to determine whether it's structured or unstructured. We're going to be talking about structured big data today. That is, records that can be read from machines or sensors or data processing applications or created by a computer versus, free-form type data, HTTP documents, for example. We're not going to be dealing with those. So we're talking about structured data. And basically, anytime that the database becomes too large for a single server, then you're entering big data territory, right? So it might be that your data set has grown too large and your indexes no longer fit in memory, or it might be that you simply have so much data that when you want to query all of it, it becomes too long, maybe 24 hours to run a single query, and that just is not acceptable. That's when the traditional data processing application, the database, becomes unusable. So machine-generated data is usually generated 24/7 around the clock. You can think of it as sales, marketing data that's collected at a supermarket, or energy meters, or any other sort of sensor that's collecting data typically around the clock. The data usually grows fairly quickly. Big data typically not only is large, but it's growing at a rapid rate, so you need a way to handle that growth. And for machine-generated data, bulk loading is very common. So there's not a lot of individual access to one or two records. Typically, things are done in bulk. So this bulk loading and then querying on large amounts of data is an OLAP pattern, right, or analytical queries. Keep in mind that if you have a lot of data, doing an alter table is going to take a long time, no matter how you slice or dice it. So you want to try to make sure that the data format or the table structure that you use is going to be the data structure that you're going to use, right? Don't plan on altering your tables all the time. A column store, like InfoWrite, is actually great here. It's a compressing column store, so you can get 10-to-1 compression fairly easily, and you can access the data much quicker because it's in a compressed form. Also, for machine-generated data, star schema is very common. Either just one big table, and that's just it, one table for all of the data, or one table that contains most of the sensor data, and then smaller lookup tables called dimension tables to store information about the records, like a list of machines or a list of stores, those kind of things, small lookup tables, whereas the collection of data from the sales machine, the item barcode, so the item number and the price and the quantity, etc., all go into the larger central table. Some other examples of machine-generated data are call detail records. So these are the records that the phone company has, or the online voice over IP company has, that record, when a call started, when a call ended, was there busy, etc. Quick, and you may run out of space on the single server very quickly if you're trying to analyze all of your call detail records at once. As I said earlier, a large online retail sales system, right? Walmart, they get a itemized receipt for each sale, right? So they also want to go back and analyze all of their information. And other things on the data by analyzing it. So analytical queries are big focus here. Human-generated data is a bit different. It can be just as big, but it's typically updated or changed, right? You can't go back and change a tweet, but you can go back and change a Facebook post or a blog post. So it's data that's generated by a user, and then the user oftentimes can do all kinds of things with that content. Same goes with an auction. There's an auction for a particular item. There's a history of bids. Those are typically updated, but it still is user-generated content. So once again, this data is often generated 24/7. It grows very quickly, and it's also updated frequently. And you can't just say, star schema models it very well. The data model is going to vary. The query pattern here is OLTP. It's online transaction processing. So small amounts of data, the person's wall or some other content, or a small amount of data is written. You're just make a single write to a Facebook page. So this type of data definitely is grows very fast, and typically you're going to have to find a way to spread it over more than one machine. All right, so all of the things I just described, basically they take up too much space for a single server, or they require too many connections for a single server, or the indexes get larger than memory, so they have to be kept artificially small, right? So for the OLTP data sets, you got to spread it over more than one machine. Facebook can't run on a single MySQL server. Now, traditionally, it's been harder for OLAP because most sharding frameworks don't support what are called cross-shard aggregation, which we'll talk about later. So typically for OLAP, people have started to look at Hadoop or other solutions, but you can use shard query instead. For OLAP, basically, this becomes a struggle when a query takes so long that it's no longer effective to try to run that query. And that becomes a commonplace. Basically, your data set becomes useless because it simply takes too much time to run a single query, just because you have too much data. Right? And the MySQL queries are single-threaded. So adding cores does not help any one single query perform better. So you can't just go buy more cores and expect a long-run query to suddenly get faster. So Shard Query, the sharding framework that I wrote, supports running OLAP queries. So sharding basics. I've been told that sharding is a portmanteau of shared nothing, which makes sense. The database is lots of machines. Each machine can act alone, right? So there's a smaller subset of the data on that machine, but that data is consistent in that single machine. And there's no shared state or shared hardware except the network between the nodes. So it's different than a shared everything architecture like rack, where there's a shared disk subsystem, for example. So shared nothing. Table, or sometimes tables, and you need to split them up so that some of the data on server A, some of the data resides on server B, some of the data resides on server C, etc. But so that each one of those silos is consistent in itself. So typically there's a big table, or tables, as I said, that are sharded. They're divided up. And then there are short lookup tables that are duplicated on each of the nodes, right? So those are the unsharded tables. And you can always join from a sharded table to an unsharded table because all the data for that unsharded table has been duplicated on that node. So the data has to be divided up somehow, and you do it based on in some column, right? So the shard key is the column in a table that indicates how it's going to be split up or sharded. For example, if the shard key is customer ID, then all the rows for any particular customer will be located on the same shard together. So when I say give me star from customers where customer ID equals 30, it's going to come back and give me all the rows for customer 30. They won't be located on any other node. So there's a thing called the shard mapper, which knows which shard belongs to which particular customer ID. And that mapper determines which shard is used. MySQL Fabric and Shard Query both require shard keys, but they do work a bit differently. In Fabric, the shard key is per table, so you can have more than one sharded table, but you must specify the shard key in a function call before you run your SQL. So you have to tell the driver which shard to look up the data on. And that's based on the shard key, so you pass that in with the function. We'll give you an example of that later. Shard query requires a shard key to be declared in your configuration. I'll talk a little bit more about how to configure shard query later. But shard query then recognizes when you use that shard key in a query, and you say select star from blogs where blog ID equals 30, it knows blog ID is the key, and it goes to the right place. Or customer ID is the key, and it goes to the right place. So it actually parses your SQL, whereas Fabric does not. That's a big difference between Shard Query and Fabric. So here, talking about the blog site, there's a blog site that has blogs is the one table. That's a primary table. Blog posts, which lists posts to some person's blog, and blog comments. Now, normally blog comments just links to blog posts through the blog post ID. But if we're sharding, we need to make sure that the blog comments go into the right server. So we'll have a minor denormalization of data, and we'll put the blog ID into blog comments as well. So blog ID will be referring back to blogs and blog posts. And over on the right-hand side, you'll see there's an unsharded table, and that's called moods. And the unsharded table doesn't have blog ID in it at all. So it's going to be duplicated in these sharding frameworks on all the nodes. Here's a fairly simple query, figuring out how many different moods have what count on a particular blog. You'll see that the blog ID is the shard key. It's used to join the tables together. And then finally there's group by. Now this query would work on either Fabric or on Shard query. If you're on Fabric, you'd have to specify the blog ID equals, well, you have a variable called blog ID probably, and that variable equals 30, and you have to associate that to the specific shard with the connection parameter. And I'll show you an example of how you do that later. But this query would work on either Shard query or on Fabric. Now, if you took away the where blogs.blog ID equals 30, it wouldn't work the same on Shard query and Fabric. On Fabric, it would still run on one node. You'd still have to tell it to go to a specific node, like blog ID 30, and you couldn't aggregate across all the different blogs like you could with Shard query. So Fabric has two different mappers. Remember, the mappers are how the framework figures out which server holds data for which key. Right? So there's a hash mapper. Right? It just round robin distributes data around the cluster. So it's not very interesting. It's also not probably used very often because it means that you can't renumber your shards or add or remove shards or split shards because it's a hash. You'd have to reload all of your data. So range mapper is much more commonly used with Fabric. It uses predefined ranges of column values to limit which server gets which rows. Right. So, for example, 1 to 25 can go on server 1, 25 to 60 goes on server 2. I'll show you how that works later. So as long as you specify the correct shard key in the function call, you'll send the statement to the right server. So here's an example of the hash mapper. Right, so customer 100 goes to the first shard, 200 goes to the second, 300 goes to the third, and then 400 goes back to the first shard because it's just a round robin. So it's column value modulus the number of shards. That's used to the shard ID. So very simple. Shard query also has two mappers. The first is a hash mapper that works very similarly to MySQL Fabric's, so it just spreads data evenly around a set of shards. Or a directory mapper, and this maps a particular shard key to a particular shard using a lookup table. Right. So when we say customer ID 30, it goes to lookup value 30 is mapped to shard 2. So shard query loader knows when you're loading into a table that contains the shard key, and it will send the rows to the right shard when you're loading data. It also supports insert, including bulk insert. So if you use that to insert rows, they'll end up at the right shard as well. So this is the directory mapper. Here you can see instead of being round robin, two of the customers have been mapped to shard 2. 2 customers have been mapped to shard 1. And there's nobody on shard 3. You can see the example mapping table down at the bottom. The real schema for the mapping table in shard query is more complicated than that, but this is a basic example. So both sharding frameworks have a shard key. Both sharding frameworks have a mapper. And together those control where the data goes on each shard. So I'm going to talk about the two main sharding frameworks. I'm going to talk briefly about MySQL Fabric, and then we'll talk about Shardstory. So MySQL Fabric is written in Python, and it's included as part of the MySQL utilities. So you can go to do dev.mysql.com, click on the MySQL utilities, and download MySQL Fabric. It's now GA. It stores configuration information in a MySQL database. So you need to have a particular node, the global node, set up to store the configuration information. And your driver, your connector, has to support MySQL Fabric. So the examples that we're going to give here are Python, but there's also Java and PHP connectors. And I don't currently have any examples of those other connectors, but I can probably get some for a follow-up blog post. And Fabric is good for OLTP workloads. Right? So OLTP, reading and writing small amounts of data, but the indexes need to be kept smaller than RAM. So you'll probably end up having to use more than one server, hence Fabric. A group in Fabric is a collection of MySQL servers, and one server can only be in one group at a time. The global group is the special group that you can write into to create tables and update shared tables. So any of the global group, the node that's the primary in the global group, is the replication master of the other servers in the setup. A node is a running Python instance, so it's the XML RPC server. And a shard, you have to specify shards in the configuration. They're a horizontal partition of data in a table. So you typically are going to use the range mapper, and so I'm going to show you how to do that. There's a primary, and that's a MySQL server, a group member, that's been designated as the master or the writer. And secondary servers are servers that can take over for a primary. When you add servers to a group, they default to being secondary. So when you actually create a group, you'll have to promote the server inside of it. So Fabric creates groups. Well, you create groups of servers in Fabric. You can have high availability by having secondary servers along with your primary servers. It uses managed replication. It requires GTID, so you have to enable the new global transaction ID settings in MySQL, and it requires log slave updates be on all of the slaves. It's not suitable for OLAP because queries always have to run on a single shard. You can't do a count star from sharded table. You can, but you'll only get the count from a single shard. You have to then go to each and every other shard, get the counts, and then put them back together. And that's what shard query does automatically. So management is via a command line utility, MySQL Fabric. You put MySQL Fabric, group, create, etc. I'll show you some of the syntax. So Fabric sharding requires a global group with the primary node, one group for each shard. You need to know the configuration of the sharding range boundaries. So, shard 1 is going to go 1 to some boundary. Shard 2 is going to go to some other boundary. And you have to modify your application, right? So you have to call that function call to set the shard key before you go and do any operations. So here is an example of adding groups. So the first command here, MySQL Fabric group create salaries global, creates a global group. And then the second line here creates two other groups, salaries 1 and salaries 2. Then we have to add a node to each of those groups. So we add servers, node 1, 3306, then the first, and then node 2, 3306 in the salaries 1, and node 3, 3306 in the salaries 2. So we have a MySQL server assigned to each one of the groups. But as I said, they're all added as secondaries. There's no primaries, so we have to promote each of the groups. So this MySQL Fabric group promote salaries global, and then MySQL Fabric group promote salaries 1 and 2. Then in order to use sharding, you have to create a sharding definition. So MySQL Fabric sharding create definition range. It's going to use the range mapper in the salaries global group. Then you add a table, right? So MySQL Fabric sharding add table to group 1 employees dot salaries. That's the table, and then empno is the shard key. Then you have to actually add the shard definitions to tell it which ranges are possible on each of the shards. So MySQL Fabric sharding, add shard, group 1. The first group, salaries -1, slash, and then the lower bound. So it's going to have 1 to whatever the next bound is, then comma, salaries -2 is the second group, slash 25,000. So it's going to end up that salaries 1 will have empno 1 to 24,999, and then salaries 2 will have anything 25,000 plus, and state enabled. And that will immediately make that sharding definition stick, and then you can edit your application so that the queries go to the right shard. So you have to specify read-write or read-only type of connection. You have to also specify the shard key. So here you can see fcnx.setProperty tables for the employees.salaries table, key equals empno, and that's going to be the variable empno, and mode equals fabric.mode read-only. And here's an example from one of our blog posts. It picks a random employee number and random salary and random times, and then it sets the property employees.salaries, keys empno, empno's that random number. So that is what tells Fabric which shard to go to. And then mode read write, open the new cursor, and then execute an insert. Right? And that insert will go to the correct shard because of the fcnx.setProperty call that was made 2 lines above. So that's all I really have to say about Fabric. It's great for OLTP. So if you have a quickly changing very large data set, it's a great solution for you. Shard query is written in PHP, whereas Fabric is Python, and it's part of Swanhart tools. Swanhart tools includes shard query, FlexFuse, and they have BC Math UDF, so that you can do precision math in MySQL to any degree. Shard query is designed for OLAP, not for OLTP. I'll tell you why. It uses Gearman for parallelism. It, like Fabric, stores its configuration in a MySQL database schema. So that's one of the first things you need to set up when you set up Shard query. And it works with any MySQL compatible database, but MySQL 5.6 or MariaDB 10 is recommended because it supports the partition hint, and I'll talk about that more in a little bit. I said that Shard query uses Gearman. Gearman is an anagram for manager. It's a lightweight job manager. It basically just listens, has workers that hang off of a queue and listen for work to come in. So as soon as work comes in, the workers execute the job, and then they can return results optionally to the client. So Shard query has Gearman workers, and it also has a Gearman client for sending commands through Gearman. So it has the worker functions that hang off of Gearman and answer the queries that you send to Shard query, insert them into a coordinator table so that they can be processed further. And I'll talk about that too. There's also loader workers and Gearman API workers. Now, the reason that it's designed for OLAP is that primarily it can run queries in parallel. Right? It treats each shard as a standalone server and executes on each shard in parallel. And it also can use MySQL partitioning. So if you partition your table by hash or by key or whatever, it can use each of those partitions to execute a query in parallel. So when that's combined with the parallelism just on running more than one server, it's a big speed up. Note that it can be used on a single server with no partitioning. I'm not going to really talk about that, but it is possible to just use it on a single server. Let's say I recommend that you use 5.6 or MariaDB 10. The reason that it's not good for OLTP is that it has to take and do multiple round trips to answer your query. It has to go ask the information schema about what partitions are available, etc. So it takes extra time to run a query. It also always has to use a temporary table, so it's better geared for analytics, OLAP. And 0.025 or so seconds is probably the minimum latency that you can or you'll find happens. There's 4 different interfaces. One is a transparent proxy. So there's a Lua script that works with MySQL proxy. It varies from MySQL in just a few minor aspects. For example, insert returns a record set to tell you how many actual rows were inserted. Because the if you insert data into a non-sharded table, it has to be duplicated on all the shards. So one of the one row ends up resulting from that single row insert. There's an HTTP interface which allows you to configure shard query and also run queries. There's a Gearman interface, and there's the PHP object-oriented interface that is the interface that the run query example program uses. So this can do select count star from sharded table or any very complex queries as well. There's a virtual schema that's defined from all of the nodes in the configuration. So basically, it treats all tables as if they're in a single big virtual schema. It has basic support for window functions, which MySQL doesn't have, but Shard query does layer on top. And it works great with a star schema, right? Because you're going to have small lookup tables and one big table that can be split up evenly over all of your nodes. To set up Shard query, it's pretty simple. You create a bootstrap.ini file. There's an example, bootstrap.ini, and that example contains all of the options that are available in Shard query. So you can turn them on or off. then put any of the specific options that you want into the configuration, and you also have to provide the list of shards in the INI file. Each one has a name, so you just put a section for each shard. It's very simple. Then you execute install config repo to install the configuration repository, and then you execute setup virtual schema with the Bootstrap INI you created to actually populate the settings into the config repo. Then make sure Gearman is running and start query Gearman workers. There's a stop workers script to kill all the workers. So as I said, Shard query supports treating the whole data set as one big virtual schema. So select count star from sharded table does work, and it executes in parallel, right? Multiple count star are combined together with sum to produce the final count, right? So that's the sum of all the counts is the actual count. I'll show you an example explain plan that makes that clear. You'll use count distinct, which is another supported aggregation function. All the major aggregation functions are supported, and there's even custom aggregation functions possible. So you can write your own aggregate functions with shard query. So shard query takes and examines all the tables used by your query and determines if they are partitioned, because it can use partitions for parallelism. If they're partitioned, a parallel plan is created where each partition is examined individually, and they can examine more than one partition in parallel. But for this to work, all of your tables must be partitioned identically. Right? So your schema should be the same on all of your shards, regardless. So your partitioning should be the same. If you are sharding by customer, you might partition by order date, or by customer ID, or whatever seems to make the most sense. But probably order date would work really well. So this is a shard query explain plan. So you can see there's select count distinct, a low order date key from line order. It realizes that the count distinct has to be turned into a group by query instead. So it selects a low order date key and groups by it, and it gives each expression a unique alias. And then at the end, you see where it says select SQL to send to coordinator node. That's the final aggregation. Right? So it counts distinct, that expression that was assigned from the temporary table. Right? So the temporary table is going to contain the distinct order date keys. You'll also note that there are partitions being used. So this table has been partitioned into 8 different partitions, and you can see that there's one query that will go to each one of the partitions. The 2 through 5 are omitted, but all 8 of those queries will run in parallel. Finally, the count is returned, count distinct 2433 in 1.20 seconds, which is pretty good. You can think of this as map reduce. The SQL to send the shards are maps, and they all reduce into a final query in the final aggregation step. This is just a quick demonstration of why parallelism makes a lot of sense. If you had one server, even a very powerful server that can just run a single thread, it'll have to examine all of the data, and it'll take a long time. Here we have 64 seconds, essentially, if it takes 1 second for each block to be examined. Whereas if we can operate in parallel, even if we have weaker machines, those machines can work on a small amount of data individually in parallel and get done in only 8 seconds. Right? So 8x parallelism for 8 workers. And that's the idea behind the query parallelism in shard query. Each green line could be a shard or a partition. There's also window functions. Window functions give a way for a query to access other rows in the result set of the query. Right? So you can look backwards or forwards and run aggregate functions on those sequences of rows. It's kind of like a self-join, but it's specified only in the query. Shard query supports window functions that stand alone. So you can't multiply something by a window function or add two window functions together. You have to use a subquery in the from clause in that case. So that's what I did here. I select SS, that's a window function, result times 4 from, and then select dep name salary sum salary over partition by dep name order by salary. And what that's going to do is do a running sum. So the first two rows have a salary of 4,200, so they group together for a running sum of 8,400. Then in the salary of 4,500, and 4,500 is another duplicate, so that's 9,000 plus the previous 8,400, so 17,400 for the second sliding running sum, etc. And so that came back in 0.04 seconds, pretty fast. Very small table. There's also a parallel loader. So you set up loader nodes to distribute the load over multiple machines. Then you load from a network file system or S3 or a web server. And you use load data in file to actually start the load. And you can specify an S3 path and an HTTP path. And optionally, there's a new option called chunk size. And you get chunk size 128 megs. This is because the parallel loader goes across the network and seeks chunk size chunks to find offsets for where to load each of the chunks. So you want to set the chunk size to a large value if you're doing a remote load, so you don't make too many round trips on the network. Finally, some tips. Stick to one big table. That's going to be your best bet, especially with compressing storage engines like InfoBright or TokuDB. Keep your unsharded tables small because they have to be duplicated on all of the shards. Pick a shard key that's evenly distributable, like some invoice date or a customer number or something that's going to spread your data evenly. With shard query, use the directory mapper if you want to split shards. Splitting shards is a manual process, but you can do it with a directory mapper. With Fabric, it supports range splitting as long as you have the range mapper, so you can split your shards in the middle somewhere. And if you're using shard query, partition all your shards identically to take full advantage of parallelism. And that's all. We can take some questions.
Hi, Justin. Can you hear me okay?
Yep.
Okay, great. Audience, just go ahead and enter any questions you have for Justin in the GoToWebinar control panel, and we'll take whatever we have here in the time we have left. All right, so Justin, the first question is, after creating the shards with Fabric, how do you import data? Can you use MySQL dump and MySQL client to load the data?
Not easily, because you have to specify in that function call each one which shard to send the data to. So you basically would have to take apart the bulk inserts that the mapper usually, or the mapper, sorry, the dumper usually out, and you'd have to run them individually and call that function call between them. So that's one of the things that's never been really clear to me, is how you're supposed to load or back up to restore through the sharding interface, and you really can't. For backup and restore, you just think of them as individual databases, and I'm not aware of any way to use load data in file or bulk loader to get rows into the shards.
Okay, the next question is there parallel execution of insert, update, delete?
No.
Okay, that was a quick one. Okay, let's see. On which node will the temp table with the aggregation be created? As I understand, this has some overhead.
It does add a little bit of overhead, but overhead. It's typically a small table, especially if you're doing aggregation. But one of the nodes is picked at random, so you can any one of the nodes acts as the coordinator for a query. Or you can, in the config table, specify that a node's not to be used for coordination, and you can specify like only one or two nodes that are particular for that.
Okay, here's the next question. Is there any practical limits with shard query in terms of numbers of partitions, number of shards, size of result set, etc.? For a popular blog site, for example, I'm imagining trying to find the 1,000 most popular blogs could become problematic as the amount of data in shards increases.
Well, when the group by results are coming back, they're actually insert on duplicate key update is used. So the number of rows that are in that temporary table are going to remain small, even though the query is aggregating a lot of rows. The practical limits, number of partitions, as many as MySQL supports, but if your data is not in memory, you're going to get not as good performance as if it all fits in RAM. But you know, it depends on your that really. There's also no upper limit as to the number of shards. They're all going to be run through the Gearman queue, and so what you'll have is workers running on each one of the nodes, if possible, and the total number of workers will limit the amount of work that could be done in the entire system. It becomes a FIFO queue, basically, of queries run in the system. And so the number of shards is, I would say, probably 1,000 or so would probably be the upper limit, because when you make changes like insertions, they have to be made on individual shards. So you don't want your shared tables, the maintenance of those, to become very, very fragile. So that the more shards you have, the more likely it would be that a insert failed on one of the shards, and you'd have to manually fix up that schema using something like PT table sync. So it's probably best to keep the number of shards relatively low. Like 256 to 1,024 is probably the most I would use.
Okay, and I apologize if you addressed this already, Justin. About shard query, what is the size limit for consolidation of the results, and what are the variables?
They all go into a temporary table, so I mean, it's a real table. It's temporary in nature. But the results go into a table. So, you know, if you did something pathological like select star from table, and that table is a sharded table, it would try to insert all the rows into that temporary table until it would eventually run out of space. Right. So you do have to be careful that you don't run queries that will use a lot of rows in the coordinator table. Right. But like I said, if you are using group by, then the number of rows stays artificially low based on the number of groups in the output. Right. So if you have 1,000,000 groups, you'll have 1,000,000 rows in the coordinator table. Make sense?
Okay. Are there any other questions from the audience? Because I think that we have come to the end of the list of questions so far. So while I just give my talk about the next webinar coming up, go ahead and if you have any more questions, go ahead and type them in. I'd like to thank you for attending today's webinar. Justin, thank you very, very much. The next webinar that we're having is on October 8th. Peter Zaitsev, who's our CEO and founder, is doing a presentation on solid-state storage. And it's all about what you need to know to optimize performance. So that will be a good one too. In addition, when I send out the, I am going to be sending out a link to the recording and the slides, so you'll all have a copy of that. And I think that's pretty much it. I see there are no additional questions. So with that said, Justin, again, thank you very much. Audience, thank you so much for your time today, and we hope to see you on a future webinar. Take care, everybody.